two examples, and let's make sure, let's make decision, let's determine whether they are under thermodynamic equilibrium conditions or kinetics process. So the first one is we call a surface. We have a curved surface. We have the curved materials, and first of all, we need to determine whether these materials or the system are thermodynamic equilibrium conditions or not. And what's your opinion? And the second example would be the case we just mentioned is a grain growth. But here we have pictures. You can visualize the grain growth, and the diameter of this grain get bigger and bigger, and some grain just get smaller and finally disappears. So this is the grain growth. So first of all, let's take a look on if you have a curved surface, is this a thermodynamic equilibrium state or not? So based on this idea, so probably my suggestion is you can write down the definition for thermodynamic equilibrium. The first of all is no spatial variation in chemical potential. So in this case, it, if you have are there any spatial variation in chemical potential? So probably we need to assume there's atoms at the convex region here. And what is surface chemical potential? So its surface chemical potential can be written as mu A0 plus, this is the chemical potential of atom A on flat surface in pure materials, plus the extra term, which included the gamma is a surface energy, omega is the average atomic volume, 就平均原子体积，然后表面能乘上平均原子体积 and times the kappa 1 plus kappa 2. And kappa 1 and kappa 2 are the curvature. So what is the kappa 1 and kappa 2? Yes, they are curvature, but what this means? So when you describe a surface, two orthogonal curvatures are used, which we use as kappa 1 and kappa 2. So we have, so the atom A at this convex region is surface chemical potential can be written as mu A0 plus a positive term. But in order to know whether there's a different chemical potential on this material system, so we can take a look on the location in the concave region is here. So the surface chemical potential of the atom A at or on this concave region can be rewritten as mu A0, the same as this one, but um, but in the concave region, we use a minus and gamma omega also plus or gamma kappa 1 plus kappa 2, the same, but this is positive. You ended the positive term, but you minus, and in the concave region, you minus a positive term. So based on this, these results, we know the surface chemical potential in this material system, especially on the surface, are varied with the curvature. So in this system, we do have a spatial variation in chemical potential. So for sure, um, this is not the thermodynamic equilibrium conditions, or this is not a thermodynamic equilibrium state. So as long as it is not a thermodynamic equilibrium state, so then that probably is a kinetics process. So we need to figure out in this systems, do we have a driving force to drive the flow process? So as we mentioned before, the surface chemical potential gradient can serve as a driving force to drive the uh, atoms at with a high surface potential energy move toward to the site with lower surface chemical potential. So the atom will move from convex region toward to concave region. And how fast or how fast it moves will be depending on the diffusivity of this atom A. And finally, it can lead the minimization of surface chemical potential. And the other example here would be the grain growth process. And what we have here is, as we mentioned, we have a polycrystalline material. So we have lots of different grains, and also between two grains, we do have a grain boundary. And as time increases, we can visualize the grain growth. And some small grain disappears as increasing time. And here we know that the energy, we first of all, we assume that we do have the isotropic grain boundary energy, which means the grain boundary energy everywhere, as long as on the grain boundary are the same. And this is, we assume that, but as we know, the energy of grain boundary is much larger than the energy inside the grain or off the grain. So which means that as long as the system tend to be minimized, then the portion or the volume of the grain boundary need to get smaller and smaller, and the portion of the grain should be increased in the meantime. So how fast or how slow um, regarding to this grain growth will be depending on the diffusivity of the atom inside the grain or into the grain boundary. So finally, it will lead the minimization of total energy, and we believe the grain boundary energy per unit volume should decrease. So that will lead, so which means that the total grain boundary area will decrease in the meantime. So that will lead to the grain, which means that you do have less and less grain boundary area, which means that you do have more and more grains. So grain turns out growth. So this is the phenomena we visualize the grain growth. So also it's a kinetics process. And we do have the driving force and also the system inertia of system, also the diffusivity of the atoms. So let's uh, uh let's go back to answer the beginning's questions. Are these cases in the thermodynamic equilibrium state? No. Okay, and layout belongs to kinetics process, and we can easily to find out their driving force and also the system inertia or mobility of the system. And take a look here. Regarding to the inertia of a system, we can visualize the inertia of the system is highly related with is directly related to material property, right? Is a diffusivity of these materials or atoms. Okay, so let's move forward. So I'm also want to give you the other case is regarding to phase transformation, and what we have here is we have alpha phase and also beta phase. So based on the free energy versus the reaction coordinate, we observe that the energy, the Gibbs free energy of beta phase is smaller than alpha phase. That leads alpha phase finally will convert it to beta phase. And how much, and based on the thermodynamics, it will go this way. But we also need kinetics to tell us how fast or how slow how much time it takes, right? So related with the activation energy, or some people call it as energy barrier. And we spend lots of time to talk about there are two factors, which is the driving force and the other is the inertia or mobility of the systems. These two factors will determine the rate of this kinetics process. So let's give you an example as well. Uh, phase transformation, for example, like the diamond. Diamond composed of the, like a sp3 carbon, right? And as we know, the diamond is metastable at 1 atm and also at 300 K is metastable, which means that sp3 carbon is metastable. And which is stable, actually, as we know, is sp2 carbon bond is much stable than sp3 carbon at 1 atm and 300 K, which means that sp3 carbon diamond is here and graphite sp3 carbon is here with a more stable, lower energy compared to diamond. And so, based on this idea, we can say diamond finally were converted to stable graphite. But how much time it takes? Finally, right? But how much time it takes? Because most of us haven't have chance to visualize our diamond ring converted to graphite, right? So, which means that the energy barrier for this phase transformation from allow diamond to graphite is pretty high energy barrier. So that lead with most of us haven't have this chance to visualize this phase transformation. So this also point out the energy barrier is the key factor to determine how fast or how slow this kinetics process is. So lots of based on this idea, so lots of scientists to want to speed up their experiments to have higher production rates for the product. So their idea will be go this way as long as they applying the driving force, no matter it's a temperature gradient or electrical potential gradient or chemical potential gradient, no matter which driving force they have or acting on the material system, in order to speed up all these reactions or phase transformation, they try to lower the activation energy to speed up their reactions by ending catalyst is is uh one of the choice. The other one is how about uh we just try to increasing the environment temperature to allow all the reactants have more energy, which means that more atoms can overcome this energy barrier. So when you increasing the temperature, that will allow more reactants have energy which is higher than activation energy. So there are two ways to speed up your experiments. In summary, ending the catalyst to lower the activation energy, or increasing the environment or working temperature to allow more atoms to overcome this energy barrier. Okay. So this is how we can tune our chemical reactions to speed up or easy say just speed up your reactions, right? Besides this, we know that the activation energy or energy barrier is quite important because it will dominate or determine the reaction rate, right? The other I want to mention, or the last part I want to mention, would be the kinetics resistance or regarding to the transport limitation. So this is one thing you need to keep in mind. And I'm going to give you an examples to talking about some reactions is not just one step reactions. Probably there are two steps reactions. So how to deal with that, or what kind of um, limitation or concern you need to take it into your mind. So I'm giving you an example here. Now I also have small ice cube. I put them into the isothermal container here. And the other one, I prepare a larger ice cube. But now I just put them into the glass without any thermal isolation, just regular glass. After a while, what happened? Which one uh will melt, fully melt? Which one will fully melt earlier? So probably the result is the small ice cube put in the container with thermal isolation. After a while, um, the ice cube gets molded with some water, but the one, although with a larger ice cube, but finally they fully melt into the water. So what happened here, or what's the difference here, or what's the idea pointed out? So we want to point out that the transport limitation. So this process actually, this kinetics process actually included two steps, which included the thermal transport and also the atomic transport in the meantime. For example, like the ice, as long as the ice cube absorbed the heat, then it's melt, right? It start melting. So let's two-step absorb the heat from external or from the environment. So this is regarding to thermal transport. For this case, because there's no thermal isolation, so this large ice cube can absorb the more heat. That will allow this ice cube quickly melt into the water, can absorb the more heat compared to this one. So the rate of ice melting is determined by thermal transport in this system. This case absorbed more heat, so thermal transport dominates this process. Because for ice transport, which means that the atomic diffusion melting process, actually they are same type or same kind of ice cube, so there's no big difference in this case. So there's some kind of like you need to consider them as in series reaction. They absorb heat, then melting. Okay, so I'm going to give you a quick summary for kinetics. Kinetics process actually we need to consider as a time-dependent state change process for a system out of equilibrium state toward to equilibrium state with specific paths and have its own corresponding rate. And there are two key factors to affect the kinetics process. The first one is driving force. Driving force here can be the temperature gradient or electrical potential gradient or chemical potential gradient. And the other is we call it inertia of a system or transport mobility or resistance of the systems. And when you uh, consider or when you have your interest in kinetics process, you need to think about that. Are there only one step reactions or more or two or more steps reactions? As long as they are that is not only one reactions. You need to think about if there are two reactions, what's the relationship between these two reactions or two steps? Are they in series or in parallel reaction? For example, like the one I just mentioned is a melting process that belong to series reaction because first of all, you need to absorb the heat from environment, then melting. Okay, the first step, absorbed heat, is regarding to the heat transport. And the second step, melting, is just melting, right? It's the H2O, the water, converted its phase from solid state to liquid state. So they are in series. So we absorb the heat and the melting. And regarding to a parallel process, what is a parallel process? For example, like the catalyst process. You add a catalyst to lower the activation energy, but inside this beaker, they still have the other path with a higher activation energy. So we do have two paths for the reactants in the same time. So we call a parallel process. 所以在这里的话，就是速率决定。当你发觉你有兴趣的动力学过程，事实上你还需要决定它是一个步骤或者是两个步骤。那如果是一个步骤，我想就是相对比较简单，你就可以看这两个是判断这两个，比如说 driving force 跟它的 transport mobility 或 inertia，就可以知道，就可以判断它的快慢，就会有一些 idea，找出它的什么是它的 driving force，什么是它的 system inertia。但如果它是两个 step 的时候，就需要先确认他们是串联或者是并联反应。那如果是串联的话，那要比较谁快谁慢的时候，就要先拆解它说，那它是哪两个串联？那像我们刚刚讲到的融化，它就是先吸热，然后再从固态变液态。那这两个就必须要拆解来思考。那如果是并联的话，那就比较像是刚刚讲的，如果你在一个你想在一个烧杯里面，然后它里面已经有反应物了，然后你帮这个反应加上catalyst 催化剂，那也就是说，在这个杯壳里面，它同时有两条路径，然后拥有不同的 activation energy，那这种它们两个就会是并联反应。那如同大家过去知道的，就是串联反应都是慢的主导，然后并联反应的话就是会是快的主导，对不对？是它的速率决定步骤。所以 rate determine step 是哪一个？就在这时候，就是你需要拆解它，然后就会知道是哪一个。所以只要是 two step 的，就会比较复杂一些，需要知道它的关系，然后才能猜是谁主导整个动力学反应所花费的时间。然后最后一个的话就是刚刚讲的 Boltzmann 的 Maxwell Boltzmann 的 distribution，这个应该还好，就是大家要知道说 thermally activated process，它是 obey 这个 explanation 的这个。那 thermal energy 我们通常都会用 KT 来做一个预估，所以这个是还好，这个没有什么特别。OK，so we ended here